So this application begins with looking at bicycle maintenance. Now, bicycle maintenance requires the bicycle to be lifted off the ground, right? It allows for easier access to remove things like wheels, adjust derailleurs, which are those mechanical components that help shift the chain up and down the gears, and to check shifting. So bicycle tool manufacturers and bicycle OEMs, they recognize this need to raise the bicycle, and they've met this need by providing bicycle stands, like the one from Park Tool here on the image on the right. These stands, though, they're large, they're expensive, costing anywhere from like $200 to $500. And because of the clamping mechanism that secures the bike to the stand, they may not fit all bike frames. Now, I'm someone who needs a bike stand, but the price and the size, they're kind of preventing me from buying one. So the other day, my bicycle was leaning against the countertop in my kitchen, and I noticed the bicycle frame's top horizontal tube, it's almost the same height as the cantilevered edge of the countertop. And I began to wonder if I could use the countertop to provide the height needed to lift my bicycle up to do maintenance. But if only there was a part that could clamp these two together. This is where Markforged comes in. So Markforged owns a patented 3D printing technology where continuous fiber can be inlaid between the layers of a 3D printed composite base material. And this results in a really strong 3D printed part. And because I have access to a Mark II in our office, I started putting ideas to paper. Yeah, literally, I started putting ideas to paper. This is how many designs begin, right? You can see I have some rough measurements in here. I made some annotations, just some things to kind of help flesh out the design well enough to start the CAD model. And this is what I came up with. It has a clamping mechanism to secure the part to the countertop's edge. And I call it an adjustable bicycle lift because the beam right here, it supports the weight of the frame and is adjustable to account for different countertop or table heights. But now to get to this point, it's not really as simple as just translating the design from paper to CAD. Designing with the intention of 3D printing requires knowledge of certain design principles. And these 3D printing design principles are called Design for Additive Manufacturing, or DfAM. So let's look at how I use DfAM for my bicycle lift. Chamfering overhangs to 45 degrees is probably the most popular DfAM principle. The reason being is because angles from 45 degrees to 90 degrees from horizontal, they don't require supports. And support material, it creates an ugly surface finish. Printing with them takes more time, and post-processing is required to remove them. So yeah, naturally, I really don't like support material. Now, the fixed part of the clamp that you see here, it uses a dovetail set at 45 degrees to avoid support material for this very reason. Now, another big DfAM principle is splitting up parts because it can result in many benefits, such as maximizing part strength or providing modularity. Let's see how this was applied on the bicycle lift. And we're going to be looking at where the clamp, the fixed part of the clamp here, meets the adjuster's tall fixed column. Now, if these were a single part, I could have printed them on their side. Now, you might be wondering, why print it on its side? Well, simply it's for strength purposes, but we'll get into that a little bit later. I would then modify the profile of the tall fixed column so that it mates with this edge and thereby avoid support material. However, because both parts have dovetails, there's this thin neck right in here. This is a potential weak spot. Also, printing this component on its side would mean the slot for the clamp's moving part would require support material right in here and might reduce how well the clamp slides. Yeah, didn't believe me? I do really hate support material. So let's use this DfAM principle. Let's split up the clamp in the adjuster section using 5/16" hardware to bolt them together. See, now you have more design freedom, you have a stronger part, and we eliminated the need for support material. Now, splitting up parts has a sister DfAM principle that answers an important question. How do we join these separated parts together? Now, of course, there's things like adhesives and press fit options, but you can also use hardware. Hardware was used to join all the separate parts together on this lift because they help serve as reinforcers. In fact, some of the nuts used were actually embedded inside the 3D printed parts using a clever slicing feature that I'll show later. Now, trap nuts aren't always the right approach. Take a look at the clamp's fixed part right in here. The two subcomponents are printed in the orientation shown on the far right. Now, to bolt these two parts together, we need to run the hardware as shown in the center image. Problem is I'm having a hard time seeing how a trap hex nut is going to work here. Well, fortunately, hardware can be used in different ways. So for this part, slots were actually added in the clamp column's outer walls to accommodate these hex nuts. And as simple as that, problem solved. Also, I want to draw your attention. Notice that originally, this clamp's fixed column was a single part. But testing showed a little bit too much deflection on this cantilevered edge. So we ran the part in Markforged's newest software add-in called Simulation. Its built-in optimize feature guided us to split the part in two pieces to greatly reduce this deflection. We'll actually be showing Markforged Simulation in a later webinar, so stay tuned. And tolerances. Now this is something that's familiar to everyone. Yes, 3D printing requires use of tolerances as well. It's just that the values for how much friction you want in the fit are a bit different from those you might be used to seeing if you're designing for subtractive manufacturing, like for a CNC machine, or injection molding. These values here, they're printed here on this table on the bottom. On the bike lift, the clamp sliding section, right in here, it needed high rigidity to avoid the lift from flexing, so we used a zero tolerance. On the other hand, a loose fit was adequate for the bolt hole openings in here, and for the lift beam's dovetail. Now you might be asking, how do you know what tolerance or offset to use? If you're ever unsure about the right dimension, always consider printing a unit test. I said earlier that I really don't like printing with support material. Well, unit tests, these are on the other end of the spectrum. I really like unit tests. And it's because they answer these unknowns and they answer them quickly. Unit tests are these small test prints that localize critical features, allowing for quick iteration to validate a design. The tolerances for the lift beam dovetail in here and the trapped nut housing down in here were determined using unit tests. I simply isolated these features with plane cuts in CAD and I printed them each in about 30 minutes. Now you can start to see how 3D printing is all about quickly and inexpensively solving your problems. Now this slide and the next slide, we're going to be looking at the final critical DfAM principle, and it's all about orientation for strength. When you're designing, you want to consider how you will orient your parts on the print bed. Maximizing print accuracy of critical features, minimizing support material. These are two criteria to always consider, but if strength is required, it trumps everything. So let's look at the bicycle lift beam. It supports the weight of the bicycle, and I would say arguably probably needs to be the strongest component of the lift. Now I've identified two viable print orientation options here, option 1 at the top and option 2 at the bottom. Which do you think is best? Well, the way I like to try to answer this question is to start looking at the layer lines for each option. The red force arrows here represent the weight of the bicycle. So I like to think of the arrow as a chisel and the bicycle's weight as a hammer. With this in mind, the layer lines of option 2 will split right open. And this is called layer delamination, and it's probably the Achilles heel of 3D printed parts. So with that in mind, option 1 does not suffer from this problem. It will use support material, unfortunately, but remember, strength trumps all. And remember that clamp and column part that I was going to print on its side? The reason I did this was to avoid that layer delamination. Lastly, it helps to consider orientation early on. Look at my initial drawings. You'll note I started applying layer lines to each part to help me understand how I could split up the parts later to avoid delamination. Implementing fiber is a DfAM principle that is totally unique to Markforged. How you position and orient fiber in a 3D printed part is dependent on the loading forces, But the key thing to remember is sandwich panel. Sandwich panels describe adding fiber reinforcement layers to the extreme ends of your part to minimize deflection. I like to think of it as analogous to the large flats on the top and bottom of an I-beam. You're maximizing strength while minimizing material usage. The theory behind all this involves understanding area moments of inertia. I highly encourage enrolling in Markforged University's composite course because it explains all this very well. Now, there are two types of sandwich panels. You have your isotropic for resisting bending in the XY plane, and you have concentric rings for resisting bending around the Z-axis. Isotropic sandwich panels were added to the bicycle lift beam to increase rigidity in the XY plane, which is the plane perpendicular to the red force arrow shown. And concentric fiber rings were added to the Hex Bolt Key to avoid breaking in torsion when tightening the clamp or when adjusting the lift beam while under load from the bicycle. I understand that this is a lot of information to take in, so let's jump into Iger, Markforged focal cloud-based slicing software, to look at how all this was done. Alright, so when you first log into Iger via Chrome, you're presented with this library screen. It shows all the parts and all the folders within your organization. And one of the nice things about this cloud-based structure is it allows access to parts used across your manufacturing sites. And it doesn't matter if they're in different states or even different countries. You have access to all these parts, and it provides automatic software and hardware updates as well. So let's take a moment. Let's glance over here at this left pane, and let's click on Devices here. And in this window, you can monitor the printers and you can monitor the print jobs in your organization. And if we click on any printer here, right, say this X7, you can see the details of the printer. You can look at the print queue, you can look at the past print history, right? And if we click Show More under Device Maintenance, we can see the automatic maintenance schedule. So Iger tracks all the maintenance items here for your printer and will let you know when they need to be replaced. So it's all hands off. Now if we go back over to the left pane and we look at Dashboard, this window provides summary data on printer utilization, on things like material consumption, and a variety of other key metrics. Okay, so let's jump into my folder. So we're going to go back up to Library. And we're going to go into my folder, JHH Models. Okay, and let's open the Adjustable Bicycle Lift folder. That's where I did all the parts for this project. And what we're going to do is we're going to examine the bicycle lift beam that we saw on the last slide. We're going to examine it here in Iger. What we need to do to bring that model, that part, into Iger is we need to go up to this Import STL button here in the upper right corner of the screen. And from here, click Upload File, which is this blue box right here in the center. And I'll click this bike-lift-beam.stl file here, and we'll open this. And click Import STL. Now, let's orient the part according to the DfAM lesson we just had. So what we'll do is we'll just simply click on the face that we want oriented on the print bed, and it'll adjust it for us like that. And from here, we need to adjust the part's print settings. Right? So up here in this pane on the right, we have our part settings right here. Now, Onyx is that kind of dark gray default composite based material, and that's what we use for this project, so we're going to leave this. For our reinforcement material, we'll be using HSHT fiberglass. That's high strength, high temperature fiberglass. We're using that because it's what we had available for this project. And as I mentioned earlier, we have a Mark II in our office, so we'll leave the printer type set to desktop. Under Settings and Infill, we're going to leave most of these default. One of the differentiators from Markforged is that their slicer, and really all their software, it's very user-friendly. Okay, Markforged, they did all the guesswork for you. The default settings are what Markforged found produces the best surface finish, the strongest parts, the most repeatable results, and all without consuming too much print time. And I've logged hundreds of print hours on these machines, so yeah, these settings work really well. Also, with fiber-filled parts, one thing I'd like to point out, see how this is grayed? So with fiber-filled parts, you cannot adjust the layer heights. What Markforged found, for instance, with HSHT fiberglass that we'll be using, is that a 0.1 millimeter layer height works the best for the print job with that material. So you're not able to deviate from this. And infill, like I mentioned, we're going to leave all these settings default. So from here, we'll go down and click Save in the lower right. So now that this save is complete, I'd like to draw your attention to this left pane here on the side of the screen. It says Part Details. So what Iger does is it calculates things like print time, the material usage, and the cost to produce this part. Really, the key takeaway here is that everything is automated. Okay, Iger eliminates the guesswork, and it gives you the best user experience. And from here, what we're going to do is we're going to jump over to Internal View on the lower right part of the screen here. And I like to think that this is kind of where the magic happens. Okay, the internal view is where we can manipulate fiber placement, we can add or remove supports, and we can insert print pauses as well. And luckily for us, this part uses all of those. So this grayed out object, okay, this is our onyx material, right? This is the part itself, right? This purple material here, this is support material. And this little band of orange right here represents the HSHT fiberglass. So to begin, what we're going to do is we're going to delete out the pre-inserted fiber groups that Iger put in for us. So we're going to go here to the right, and we're going to delete this group here, and that removes that bit. And then we're going to delete this right here. Okay, now that that's complete, let's remove the support material that's right in here in this nut housing. Remember, the roof of the nut housing is a 0-degree overhang, so support material was generated beneath it. So to remove this, we'll go into 2D mode by clicking on 2D here in the upper right. And what we're going to do is we're going to cycle through this timeline here at the bottom of the screen. And we're going to cycle through it until we reach the last floor layer of the nut housing, which, okay, there's the nut. See, there's the support material in there. We're going to dial it back. So this right here, remember, we have 4 roof and floor layers. That was the default setting from earlier. So you see we got 1, 2, 3, 4, and then we get into the actual perimeter of the housing there. So we're going to go to this layer. This is the last floor layer of the nut housing. And we're going to go up here to the upper right, and we're going to click Create New Override. And from this drop down, we're going to click Remove Supports. And it prompts us to add a sketch. So we'll click Add Sketch. We'll go into Center Circle for this one. We could choose any, but the circle makes the most sense here. And we'll take that crosshair and we'll drop it right in the center of that bolt hole. And from here we'll click and we'll drag it out. Just make it a bit oversized there is fine. And we'll click Finish Sketch. And then from here we're prompted with this little slider option down here in the timeline. And we're going to grab the slider on the right part and we're going to drag it. And you'll see it's dragging up the layers. And we're going to drag it. We can make it a little bit oversized. We'll drag it to like layer 219 should be fine. That encompasses the full height of that support block. And then we'll go here to the right side of the screen and we'll click Reslice and Save. And we'll just click off. And there you go. No more support material in the nut housing. Alright, now remember that DfAM principle of embedding hardware inside 3D printed parts? I mentioned I would show it later. Well, this lift beam uses one. So what we need to do is we need to insert a print pause so that we can drop the nut into its housing once prompted. So what we're going to do is we're going to enter 2D mode again. And we're going to find the first roof layer for this nut housing, okay? So we're going to go through, we're going to drag through the timeline. Start from the top and work back. Go through it here. Alright, so that's the last roof layer. Remember, we got 4 roof and floors, so that's 1, 2, 3, 4, and then that. Alright, so this is the first roof layer. This is where we want to be. Okay? Now you'll notice that material is printing here, right? These lines represent material printing here. So if we were to insert a pause right here, we wouldn't be able to drop the nut in, right? There's no space for it. So what we got to do is we got to go 1 layer below, right here. Okay, layer 206. See, now we have full room, no obstructions. So what we'll do is we're going to jump up to create new override, right, up in the upper right. And at the very bottom of this selection pane, we have insert pause. We'll click that. And at layer 206 now, we have a pause inserted. Simple as that. And what we'll do is we'll go back into 3D mode. Alright, and while we're on the subject, I wanted to make a special note here. With this model, okay, whenever you're designing these nut housings for trap nuts, what you want to do is you want to make sure that you have a few layers worth of space between the roof of the nut housing and the nut itself in your CAD model. Otherwise, you risk a collision between the print head and the nut. So what you see here is we modeled a space of about 0.3 millimeters between the roof of this nut housing and the nut, which, because we're printing at 0.1 millimeter layer heights, gives us about 3 layers of space, which was plenty adequate. Alright, so now that we're back in Iger, let's start adding our fiber layers. Now, remember that we want sandwich panels, right, which are the fiber layer groups positioned on the extreme ends of the part. Because this beam is loaded in the XY plane, so we got force directed upwards right in this area, we want to use isotropic fiber layers. So what we're going to do for this is we're going to enter the 2D mode. And what you'll notice is that we always enter the 2D mode when we create these overrides. That's the proper workflow for doing this. And what we're going to do is we're going to scroll through the timeline. So we're going to go back to the timeline here at the bottom. And we want to find the final floor layer of the beam's main surface where the frame will rest. So you notice we don't want to do anything in here. So we're going to keep moving up. Okay, we need to drop a little bit down here. Okay, so here we got our floor layers, okay? So this is our first floor layer, second, third, fourth floor layer. Okay, now this is layer 74. And we can't actually add any fiber layers to these roof and floor layers. So what we do is we need to jump 1 layer ahead. And this is layer 75. We can add fiber here, so we're going to go up to the create new override in the upper right. And we're going to select add fiber. Okay, and we're going to leave these default settings. Everything here is good. We're going to jump into 3D mode. And then we're going to go back to our timeline and we're going to click this slider. We're going to drag to the right until we make 4 layers right there. And we'll click anywhere in the screen and Iger is going to load those fiber layers in place. Now, 4 fiber layers was chosen because this is a kind of a default figure for Markforged. I know it may not seem like much, but it is definitely sufficient, right? I mean, like I said before, Markforged, they've done all the research, and this is what they found works the best. Alright, so this is our first sandwich panel, and what we're going to do is we're going to create another sandwich panel on the other side, right? So as before, we're going to go back into 2D mode. Alright, and we're going to go up here, and we're going to find the first roof layer of this beam. Okay, so not quite there. Let's go a little bit down, alright. Alright, so that's our first, there's our first roof layer, okay, layer 267. And like I said before, we can't add fiber on this layer, so we got to go 1 below, right there. Okay, and we're going to go up here to create new override. We're going to click add fiber. We'll leave the settings here as default. Go back into 3D mode as before. And this time we're going to grab the little slider on the left and we're going to drag it to the left to create 4 layers right there. Click anywhere on the screen. Iger will load those panels in. 4 layers. There we go. That's all there is to it. So that's our second sandwich panel, and the sandwich panels are complete. Everything is loaded in. Alright, but we do have one more fiber layer to add though. So this beam here is bearing the brunt of the load from the weight of the bicycle, but some of the load is also applied to the trap nut right in here. So what we want to do is we want to reinforce the top of the nut housing, which is actually the bottom because this part is flipped upside down. So as before, we're going to go into 2D mode, and we're going to find the first floor layer for this nut housing. We're going to go right back in here. There it is. There's that first floor layer, 131. And we want to go one below, because remember, we can't add any fiber where there's a roof or floor layer, so we want to go one below, right there, 130. And same as before, we're going to go create new override in the upper right. We're going to select add fiber. Now, as before, we left the defaults, but this time we're actually going to change one of the default settings, okay? And that's this one, this concentric fiber ring. So there's two concentric fiber rings. You'll notice you have a ring of fiber, two rings of fiber on these outer walls here, and you've got two rings of fiber around this bolt hole. Now, these concentric fiber rings around this bolt hole, they don't serve much purpose, right? The fiber layers would be more effective at resisting the deflection if the fiber lines could run all the way up to the perimeter of this bolt hole. So if we set the ring count from 2 down to 0, we select apply changes. See, now the force of the lift beam on the nut is more unilaterally transferred to the fiber paths. So we're going to go back up to 3D. We're going to select this fiber group, and we're going to drag the slider to the left to create 4 layers. Click anywhere on the screen, let them load, and there we go. And I'd just like to make a note that this suggestion was something that I learned in that Markforged University Composites course. As I said before, it is a great course. I highly recommend you enroll and take it. Now this part is ready for printing. So we'll go over here to the bottom right, we'll click Save. And we'll go down here and click Print. So here you can see a rough preview of the part on the print bed. When you go up here on this right pane and you select Printer, drop this down, what you'll notice is that I have access to sending this print job to any printer in my organization. Right? I can send it to the Mark II in Arizona. I can send it to the Mark II in Dallas. I can also select Export Build if I wanted to save it to a thumb drive for later. Again, the takeaway is that full flexibility and ease of use is the name of the game with Markforged. And that's all there is to it. Here are some images taken during the various stages of printing and the build process. You can see the first fiber layer, so here are these concentric fiber rings around this part. In the upper left, you can see the isotropic fill lines here in this image just to the right of it. And on here you'll notice that there are 45-degree alternations in each layer. That's from one of the default settings in that fiber group in the internal view on Iger. Of course, this can be modified to suit your application if needed. And here, this is just some support material on the bottom side of that lift beam. And then these 3 images on the bottom, they represent the print pause. Okay, so when the print pause arrives, you'll receive an email notification, and then you'll be presented with this screen on your printer. And all you have to do is just drop the hardware in and click resume. It's as simple as that. As mentioned before, notice from this view, notice how the nut is totally entrapped in that housing, right? You can't even see the nut from this angle. That is just to reinforce the fact that we want to avoid any risk of the print head striking the nut and causing a print failure. And finally, here's the finished product. But I will say, pictures are one thing. Let's actually take a look at some videos coming up here to see how well it works. Alright, so here I'm setting the lift onto the table's edge. That little light brown circular pad you see there on the clamp is just a friction pad. And I'm using that printed Hex Bolt key I printed to tighten the clamp, getting it nice and tight. And There's a small neodymium disc magnet inside the key, so I can quickly just spin the key to raise the height of the lift beam without the key falling off. It's pretty handy. Okay, so now with the bike lift in place, I simply place the bike frame's top horizontal tube on the lift beam. And now you can see the back wheel of the bicycle is suspended up and you're ready to begin any maintenance that you have. In this clip, you can see I'm shifting the chain up and down the gears. As I mentioned at the beginning, this would be a necessary step if you replace the rear set of gears or if you needed to adjust your rear derailleur. And I've tried to do this before with the bike seat resting on a doorknob, and it is a pain. The adjustable bike lift just makes life so much easier. And I couldn't have done it without my knowledge of design for additive manufacturing. Not to mention Markforged's suite of industrial grade materials, their precision 3D printers, and of course their enterprise turnkey software, Iger. Thank you for joining the webinar. For any of your 3D printing questions, just reach out to us. Reach out to me for any questions or concerns, or feel free to contact me and tell me what cool projects you're working on with your 3D printer.